A student sitting in a campus lab types a URL and hits enter. That single keystroke triggers a physical chain reaction. The request dives past the motherboard, entering a vast architecture of raw electrical pulses and optical light. At this microscopic level, digital data is nothing more than voltage changes on a wire. Electricity possesses no intelligence. It has no map, no compass, and no innate ability to navigate the millions of miles of global infrastructure. To prevent that voltage from dissipating into static, an unbroken sequence of highly specialized machines must catch, interpret, and route those signals. If even one of these devices fails, the journey stops, and the screen stays blank. Far out in the wide area network, a web server responds to the student's request. It doesn't send the web page as a single file. It fragments the data into thousands of tiny, manageable bundles called packets. This animated diagram shows the anatomy of one of these packets. It is built in 3 distinct layers. At the center is the payload, a small chunk of the actual web page. Wrapping that is the IP header, containing the routing instructions. The outermost layer is the frame, engineered for physical transport. Inside that header sits a time-to-live countdown. This decreases with every stop, ensuring lost packets expire. At the end is the checksum, a strict mathematical fingerprint verifying the payload arrives on arrived. This encapsulated structure carries everything required to navigate from a server on another continent to one specific terminal in a college lab. It only needs the right hardware to read the labels. Look at this oscilloscope display. When the packet arrives at the campus perimeter from the internet service provider, it is riding a smooth, continuous analog wave. Computers cannot read this. The modem acts as the physical translator, sampling that analog wave and converting it into sharp, discrete digital squares, binary zeros and ones. Now that the signal is legible, it needs direction. The digital binary moves directly into the router. This machine operates at layer 3 of the network stack, making it the primary navigator. In this visualization, the router extracts the destination IP address. It scans this against its internal routing table, a constantly updated GPS map. It executes a longest prefix match to find the best path, locking in the next hop. Because the campus uses thousands of devices, but only shares a few public internet addresses, the router performs network address translation. It translates that single public identity into the specific private address of the student's computer. The modem translated the physics of the signal, and the router mapped the logic of the path. The packet is now aimed directly at the campus network. Before crossing into the internal network, the packet hits a hard checkpoint, the firewall. Its default function is to block data. This diagram demonstrates stateful inspection. The firewall maintains a dynamic state table of every outbound request the campus computers have recently made. The scanning beam checks our inbound packet against this memory. Because it recognizes this packet as the requested web page, it clears the checkpoint. Occasionally, networks speak entirely different languages. If the packet needs to interact with an incompatible architecture, like a legacy storage system or a dedicated voice-over IP network, a gateway steps in to completely strip and rebuild the data into the new protocol format. Having cleared the perimeter's strict security and translation barriers, the packet is fully trusted. The engineering challenge now shifts from keeping threats out to moving the data across the campus as fast as physical laws allow. Copper Ethernet cables max out at about 100 meters before electrical resistance degrades the signal into unreadable static. To push data down long campus corridors, a repeater intercepts the fading signal and generates a crisp, full-strength duplicate. As the packet crosses from the main administrative building to the student lab, it passes through a bridge. This device learns the physical MAC addresses of connected machines, forwarding the packet specifically to the correct building segment rather than blindly echoing it everywhere. In older networks, this distribution was handled by hubs. This diagram illustrates the problem. A hub takes a signal on one port and violently broadcasts it to all other ports simultaneously. When 2 devices talk at once, their waves collide on the shared wire, destroying the information. We solved that physics problem with a hardware-accelerated switch. Instead of a shared wire, The switch relies on specialized ASIC chips and a content-addressable memory table. It reads the exact physical destination and opens a dedicated, isolated electrical lane for that specific packet. By eliminating shared traffic lanes, the switch guarantees our packet a collision-free path. It navigates the labyrinth of the building's wiring in mere microseconds. If the student were sitting on the lawn, an access point would take over the final leg. It translates the wired frame into a complex array of overlapping radio frequencies, beaming the data through the air. But our student is at a lab desktop. The packet races out of the wall port and directly into the network interface card, or NIC, bolted into her motherboard. The NIC's controller chip reads the 48-bit hardware address to confirm it is the intended recipient. It runs the mathematical checksum one last time. Validating a perfect match, it strips away the transit packaging and dumps the raw web page payload straight into the system's memory. The network's job is over. At this precise millisecond, electrical transmission ends, and software takes control. The student's monitor illuminates with the loaded website. From the moment she pressed enter to this final frame rendering, only 50 milliseconds elapsed. This chart maps the complete relay race. At layer 1, repeaters and modems handle pure physics. At layer 2, switches and bridges govern local physical addresses. And at layer 3, routers make the complex logical decisions that span the globe. 10 distinct machines, coordinating in a fraction of a second. This isn't theoretical. Look at these racks. This is the physical reality of the internet. Millions of these switches and routers run continuously in massive climate-controlled arrays, processing terabits of data per second. We built this speed through decades of relentless physical engineering, evolving from isolated mainframes and tape reels into a tightly integrated global nervous system. That invisible highway extends directly into our outdoor landscapes. Giant radomes and steel telecom towers push these microscopic electrical decisions across continents and oceans. Scale this up to billions of endpoints. Every email, every financial transaction, and every video call relies on this exact sequence of hardware working flawlessly. The cloud is a convenient myth. There is no cloud. There is only a vast, meticulously engineered landscape of copper, glass, and silicon, executing this exact journey, packet by packet, every single second.